Hello everyone! This video, Why Physics Electricity, is continuation of our previous one, What Electricity. And we will talk about your potential interest to learn about electricity deeper. We will talk about benefits of knowing this topic. Please take your time to watch previous videos to briefly understand what electricity is, since we plan to use some terms from that videos. Physics Explained, and we briefly discussed it in our video Techniques and Technology, that energy is a property that must be transferred to an object in order for object to perform work or to be heated. For example, any object movements, lightning or sound producing, etc., can be considered as work, and for that we need to apply certain amount of energy. There are a lot of forms of energy around us. And energy of one form can be potentially converted into energy of another form. Another thing, people are very dependent on energy, because once we learn how to conveniently produce it a few hundred years back on a massive scale, a lot of use cases were revealed how and where to spend this energy in industrial mass production, in our daily routine, evening lights, TV, etc., which significantly improves our lives. Science and technology were evolving, and a lot of sophisticated devices and things used nowadays which consume energy of certain kinds. For example, mobile phones, computers, electrical appliances, cars, airplanes, spaceships, etc. Why we started this video with discussing energy? Because electricity is one of the forms of energy, and it can be used for electrical devices to do some work. But it's not just one form of energy among lots of others. It's a super convenient form of energy. Convenience is based on nearly immediate availability potentially everywhere where people live, and easy ways to use it. How was it achieved? Because of physical prerequisites for such convenience. It is relatively easy to transport electrical energy without significant loss on a large distances of hundreds of miles. Remember in the previous video we mentioned that using conductor materials like metals in a form of wires allows us predictably control where electricity can travel. We also mentioned that alternating current, which was discovered with high voltages for economical transporting electricity, where transformers could help to increase voltage of alternating current before transmitting over large distance. Electrical energy is transmitted nearly instantly, almost at the speed of light, which means it can be transmitted almost 10,000 times around the Earth within just 1 second. That allows to have centralized producing of electrical energy at power plants, backed up by long-distance distribution to end consumers using electrical power lines virtually to electrify any building. That means there is no need to produce energy by everyone for personal needs, because electricity can be delivered to your door. Similar way happened with food, energy for our bodies. Historically, there was hunting, fishing, gathering. Then local planting for nearby community, and eventually centralized farm producing with delivery to your local grocery store or even at your door by delivery companies. When electricity is delivered at your door, important thing is it's easy to stop delivering electrical energy right away, meaning to connect and disconnect energy-using devices. Similarly, like eating fresh veggies or fruits, once they're in your house, there is no need to spend time for preliminary prepare your energy source for quite some time. No need to start burning wood or charcoal for several minutes before grilling, or put some gas into your diesel generator. With electricity in your house, once you connect device to outlet, power starts coming immediately. It's very easy to convert mechanical and other types of energy, like solar energy, into electrical energy. That's why centralized producing of energy is possible on different types of power plants, taking different sources of input energy for electricity production: solar light, winds, oil, gas, nuclear, hydro, even outdated coal, etc. Again, physics explained ways of transforming types of energy into each other. And it's easy to convert electrical energy back to other types of energies to do actual work for end consumers. For example, electricity can be possibly converted into light, sound, video, mechanical motion, heat, cooling, wired or wireless transmission of information, and so on. Having so convenient form of energy delivered to your door consequently brought lots of devices to use it. Major ways of using electricity, for example in US, are cooling, air conditioning, space heating, water heating, lighting, refrigeration, TV and related electronic equipment, clothes dryers, computer and related equipment, and so on. In other words, convenient electricity and its consumer equipment surround us everywhere and every day in our modern life. Isn't it a good reason for everyone to be familiar with electricity physical phenomenon better? For example, to understand how much electricity is consumed in your house, not to be surprised with electricity bill. Or to assume what might be the reason of light bulb is not working. Or to ensure not to touch wires or electricity outlets under high voltage, because it might be dangerous. Moving to the next topic, consequent related phenomenon. Knowledge of electricity can be a prerequisite for learning other topics. For example, knowledge of alternating current consequently allows to learn about transporting electrical energy, or about creating and propagating radio waves, also named electromagnetic waves, which are basis for data exchange using wireless signal transmission. Consequently, it opens doors for learning about antennas, which are special devices to enhance the rate of electromagnetic radiation by using special antenna design. Let me clarify how knowledge of electricity is relevant to mentioned topics with examples. Before to proceed, I'd like to talk about totally different topic not related to electricity, but it should help to understand something to be discussed later in this video. Most likely, at least once in your life, you tried to inflate a soap bubble. You probably saw different types of bubble vents. Most often you saw small ones, with a size no larger than hands, but there are also larger ones, with a size compared to adult height. How does it work? You put your bubble vent into a bottle with soap water. Eyelet of bubble vent will contain flat, very thin membrane made by soap water. You blow some air from your mouth or using power of wind directly towards eyelet. This air inflates your soap water membrane so it forms shape of sphere, which can rip off vent's eyelet and fly away. Let me share a few observations about these soap bubbles. First one. The larger an eyelet of bubble vent, the bigger bubbles could be made. And moreover, size of bubbles is comparable with the size of eyelet of bubble vent. On average, diameter of bubble is 2-4 times larger than diameter of eyelet. But there might be some variations though. Important thing, spherical form is ideal and stable in nature, so bubble can live for a while in a stable form. Second observation, if you have enough soap liquid taken by vent and constantly blow air into eyelet, sometimes you can see a chain of several bubbles formed in a similar size one after another, which are ripped off from vent eyelet and flying away. Third one, if you put weak, slow airflow towards eyelet, then membrane won't bend enough to form spherical bubble. It will stay more flat than curved, which consequently is not enough for our underdeveloped bubble to rip off from vent and fly away. Because soap-based liquid on your convex hull would have stronger surface tension directing membrane in opposite direction to your weak airflow force. Fourth one. What about applying too strong airflow? You probably may have for a while bubble in the form of elongated sausage. Likely not a good candidate for ripping off, because it's too lengthy, too far away from ideal spherical bubble to be stable to survive. Let me wrap up. Only certain applied conditions with airflow would allow to form bubble of certain size comparable to a size of an eyelet, which could rip off and move away. Now let's turn to topic related to electricity. It was discovered that when electricity appears, for example inside a wire, this wire started being surrounded by magnetic field. We briefly started previous video What electricity with magnets which produce persistent magnetic field. They are permanent magnets originated by material properties. When we talk about magnetism appeared for limited time, for example at a time of electricity applied, we name such magnets as a temporary or induced magnets. When we apply direct current to our wire with certain constant voltage, Our electrons accelerated quickly at the beginning and then move one direction with the same speed. Remember our analogical example with chain of magnetized wagon from previous videos. So our wagons move at the same quickly stabilized speed. But classical electromagnetic field is generated by accelerated electric charges, electrons. Accelerating charges mean that they are not traveling at a constant speed, but increasing their speed most of the time to generate electromagnetic field. But how is it possible once electrons establish their cruiser speed in a wire? The secret comes when we replace direct current with alternate current. Our charge wagons start moving back and forth. When electrons surplus happened on one side of our wire, that pushes all electrons inside our wire towards the other side, increasing their speed, while voltage, difference in electrical potential between two endpoints, is increasing. Since current is alternating, at some point surplus of electrons should be applied on the other side of wire, stopping all our electrons, wagons, moving in the initial direction, then starting and accelerating their speed on opposite direction. With alternate current, every second there might be lots of accelerating of electrons in constantly changing opposite directions, which is a prerequisite for electromagnetic field to be generated. Forget for a while about generating electromagnetic field by wires under alternating current. Another separate important discovery was made. Electromagnetic field was observed traveling far away through space, propagating energy on a long distance. In this case, they use term electromagnetic radiation, or also propagating waves of electromagnetic field. Important comment. Technically, electromagnetic waves do not require a material medium for their existence and propagation. They are kind of waves of a force, which means they can potentially go away and travel long distances to other stars even in a vacuum. Electromagnetic fields and radiation can appear in nature different ways. For example, stars, including our Sun, generate a lot of such radiation. But within our topic, we are interested in phenomena related to electricity, and in particular predictable ways of generating electromagnetic fields by alternate current using convenient metal wires. And the first few questions regarding that. Can electromagnetic radiation escape from the wire where it's generated and fly away on its own? Do we need to apply any special conditions to make it happen, or it is happening all the time? Are there any other benefits from such artificial electromagnetic radiation if it's possible? Answering briefly on these questions. Yes, electromagnetic radiation can be propagated from a wire where it's generated. In this case, term far field could be used. For that, we definitely do need to prepare certain conditions, so field can escape away and start traveling outside on its own. For making electromagnetic waves propagation predictably possible and easy, special devices named antennas were invented. We will talk about them in a moment. Regarding benefits, such propagating fields allow to transmit energy carrying semantically useful information far away from source of generated electromagnetic field to receiver located miles and miles away. What are examples of using such propagation? Radio stations, mobile phone communication, satellite data transmission, etc. Let's talk about antennas. Antenna, in the radio domain, is in short a device for transforming an electric signal into an electromagnetic wave or vice versa, and enabling these waves to travel on far distances. One classification of antennas says there can be transmitting antennas for the production of electromagnetic waves and receiving antennas for reception of incoming electromagnetic waves to make the opposite job. Before discussing antennas in some details and what makes them unique to fulfill their task, let's first remind few terms. In the literature, you should be able to find geometrical interpretations of radio waves propagation as a combination of electrical and magnetic waves in a form of sinusoid perpendicular to each other. I don't plan to dive deeper about it in this video, since there are a lot of brilliant visualized explanations regarding it in the literature and internet. But I would like to mention a couple of terms related to sinusoid in general and to radio waves in particular. First term is frequency. We already mentioned in the previous video. The frequency of a wave is the number of complete alternations per second. The more such full cycles per second, the higher the frequency. Another term is the wavelength, which is the distance the wave travels in one cycle. It's also equals to a distance between the successive crests or troughs in the wave. Velocity of different radio waves should be the same in the same medium conditions. In vacuum, it will be a speed of light, for example. In the earth air, a little bit lower, but, which is important, constant for all radio waves. Constant for all radio waves, meaning literally for all, regardless of wave's frequency. As a result, low-frequency waves are long waves, and high-frequency waves are short waves. It's better to visualize it graphically. Each second, all of radio waves travel the same distance. But if frequency is higher, larger amount of cycles per second to be observed, therefore shorter the wavelength to be. Why we mention these terms? First, we are now focused on a question: how waves start their journey out of their wires with alternate current. An antenna is our device to make it happen. I think it's also better to imagine how antenna, for example transmission antenna, may work effectively in relation to a wavelength. Effectively in terms of producing intense wave with incoming moderate alternate current power applied. It was concluded that alternate voltage source brings two types of ideal antennas: a half-wavelength loop and a half-wavelength dipole. A loop looks like a single coil, a perfect circle made of metal wire. Dipole can be imagined as two metal wires geometrically looking oppositely apart. This is a symbol of alternating current generator, which delivers current to input terminals of antenna. If we talk about transmission antenna, ideal antenna means producing intense wave with the most power going away to be propagated. Antennas launch propagating fields that continuously carry energy away from the source. The energy is not stored in certain place while traveling, but propagates from the source regardless of whether receiving antenna exists or not. Transmitting antenna has no idea are there any receiving antennas waiting for any signal. Similarly, when you burn wood, heat will be escaping away, and regardless of do you plan to bring close some meat to be cooked by heating or not. Let's just try to visualize how half-wavelength dipole helps to say bye to electromagnetic waves. Remember, we talked about permanent magnets in the video What Electricity. Magnetic field outside of its magnet is initiated from North Pole towards South Pole. Similar thing happened when two opposite charges separated by some finite distance. In dipole antenna, alternate current applied to both sides, wires of antenna. Because of that, during each cycle there will be excess of electrons in first wire and at the same time deficiency of electrons in the other wire. And then charges change their place with excess of electrons moving from first wire to the second one, and same situation repeats with every cycle. That means magnetic field will be appearing, disappearing, with electric field happening and changing its direction every cycle. Interesting moment. Special construction of our ideal antenna, distance between endpoints of both wires to be half of wavelength. That makes process of flying magnetic field off the wire much easier. To be more precise, magnetic field will rip off from antenna along with electric field, so electromagnetic field will be propagated away. If we look into two-dimensional slice of our field, every cycle of our alternating current, our waves will grow like a soap bubble when you apply some airflow. Distance between endpoints of our dipole can be compared to eyelet of bubble vent, also in two-dimensional slice projection. And then charges will start moving opposite direction, helping our radio wave to close a loop and form something similar looking to a bubble. A little bit squeezed though, but ready to travel away in the direction where it was started growing. Now let's remember observations regarding soap bubbles. Remember the first one. The larger an eyelet of a bubble vent, the bigger bubbles could be made, and diameter of bubble being 2-4 times larger of eyelet's diameter. Same with antenna. The larger size of dipole antenna, the bigger wavelength of electromagnetic waves to be easier escaped from antenna away. For example, if we have one of the frequencies of US mobile networks, 1.5 GHz, meaning 1.9 billion cycles per second. The wavelength will be around 16 centimeters or 6 inches. So ideal dipole antenna size for it should be around 8 centimeters or 3 inches, half wavelength. And such antenna would help our mobile network electromagnetic waves to be ripped off and propagated away. Not always you can use ideal antenna. There might be a need for a compromise between ideal world and size where you need to put antenna. Sometimes half wavelength is hard to deliver, but anyway antenna size to be very close to that. A few times difference probably. Second observation about soap bubble was regarding chain of bubbles ripping off from vent eyelet. Similar with antenna. Every cycle of alternating current we have electromagnetic wave part ripped off when excess of electrons is on first wire, and right after that another wave part ripped off when excess of electrons is on the second wire. Since alternating current is constantly delivered to antenna, this process is constantly repeating, sending electromagnetic wave parts away, similarly to chain of bubbles while there's enough soap liquid and airflow. Third observation regarding bubbles was about weak airflow when soap membrane is not enough bended to form bubble able flying away. Similar with electromagnetic field. In terms of antenna size, you can imagine that your wavelength is extremely smaller than dipole size. Remember, the higher the frequency, the smaller the wavelength. So it cannot make more or less ideal spherical form to escape from antenna and fly away. And fourth observation was the opposite one, about too strong airflow and extremely bended soap membrane, which is also far away from ideal spherical one to escape from bubble vent. Such an example could be equivalent to way larger wavelength compared with dipole antenna size, disproportional for ripping off, survive and fly away. That's why if we could use previously discussed 3 inches antenna, which is ideal for using for 1.5 GHz signal sending away from mobile phone, it's totally not appropriate to use the same antenna for propagating electromagnetic waves for extremely lower or extremely higher frequencies. Regular electricity comes to the houses in US at a frequency of 60 Hz. What do you think would be wavelength for it? Almost 5 kilometers or slightly more than 3 miles. Our convex hull of our bubble would be too lengthy for escaping from our small antenna surface. For extremely high frequencies, on the contrary, analogical bubble to be represented will be as almost flat surface. Not a good scenario for flying away and propagating as well. Similar analogies are applicable to ideal half-wavelength loop antenna instead of dipole one. I don't want to spend time on receiving antennas, just want to mention that for receiving antennas, the tasks to be different but also relating to their effectiveness. They need to be designed to give maximum electrical signal output and a minimum noise, non-related extra signal, from incoming electromagnetic field. But similar things regarding receiving antenna size compared to wavelength is applicable, whatever we discussed moments ago. Wrapping up. In general, antennas make possible to transform alternating current into electromagnetic wave, and vice versa, enabling these waves to rip off and travel on a far distances. Geometrical features of metal-wired antennas, their size closer to half-wavelength, is the main reason making them ideal antennas. Let's move to another different scenario of using electromagnetic fields. If regular wires carrying alternating current are used, they likely don't look like ideal antennas. Electromagnetic field is still generated, but in this case, conditions are not met for this field to escape from its wire to propagate energy away. Question: is this field still contains energy? And can it be used somehow? Answering these both questions, it was observed that electromagnetic field surrounding its wire still does contain energy. But since energy is not propagated away along with field, it is instead stored at a relative proximity to its wire and can be transferred. In this case, term near field can be used for our electromagnetic field. What is the condition to transfer energy in this case? It actually depends upon what other electrical, potentially electrical or magnetic devices are in the near field. That's why you also can hear term reactive electromagnetic field. Reactive field name comes because it reacts with devices that are within it. How energy of the field can be used? Probably the most famous applied use case is an example of using transformers. Transformers are devices that not only can provide electrical energy without physical contact with initial wire, but also allow to increase-decrease voltage of an alternate current. How come? An inductor, also named induction coil made from several metal wire coils, creates a reactive electromagnetic field that stores energy surrounding this inductor. Of course, field comes when alternating current is applied to inductor terminals. When we're adding a second induction coil close enough within this reactive field, but without physical metallic contact, it allows to transfer energy to a second inductor. And this is done thanks to electromagnetic field. As a result, electricity voltage will be observed on the wire terminals of a second inductor. The more wire coils are in a second inductor, the higher voltage can be observed on its ends. Simplified as summary of generated voltages of each coil of a second inductor. That's how transformer could increase voltage of alternate current, just by adding extra coils. And if you remember from previous video, high voltage current is convenient for traveling long distances due to relatively low power loss. By the way, if smaller amount of coils used in a second inductor, output voltage of transformer could be decreased, which is useful once electricity is delivered closer to customers' houses. That was about transformer device, which is a good example of transferring energy within near field. Let's remind what we have discussed so far regarding phenomena related to electricity. When we use metal wires, we can apply alternative current, which by laws of physics generates electromagnetic field. We discussed two possible scenarios of using such fields. First one was about electromagnetic field escaping from source wire and propagating a large chunk of its power on a long distance. Main criteria for this field to escape from wires is geometrical form and size of wires to be used. And device containing specifically designed forms to enable electromagnetic field to rip off and travel on a far distances was named as antenna. Second possible scenario was about electromagnetic field surrounding wire at a relative proximity, with possibility to transfer energy without physical contact to certain devices nearby. And second inductor of transformer was an example of such device nearby. If you have been spending time exploring this phenomenon, which could help to clarify, do we have just two main scenarios, near field and escaped far field? And what are other important criteria for electromagnetic field to escape away from the metal wires? You are very welcome to reach out to me. We will see, maybe we could improve this video. We mentioned just a few phenomena related to electricity topic, but there are lots of others, linking together one after another. For example, when you understand principle of sending and receiving electromagnetic waves, you could be concentrated on how useful information is mixed with other signals before transmitting. Then topics of signal modulation and demodulation could be interesting for you. We don't plan to discuss lots of consequent terms and applied use cases. The goal of this video was to show that electricity is a very important part of our modern lives. It has a lot of related topics and resulting in lots of very beneficial scenarios for making human lives easier. There are many ways how you may touch any relevant information. Either build solid background understanding about electricity and surrounding phenomena in school, college or university, or making scientific or technological discoveries at work, or just being electrician helping with wiring house, or even head of household to understand what electrician made. Therefore, information which we briefly discussed within our set of videos What and Why Electricity would be definitely interesting and highly likely very practical for you. Hope you enjoyed our videos and will check others on our MotivationHow portal. See you!